My name's Sean. I'm a PhD student at the University of Toronto, and today I'll be talking about the paper titled The Space Complexity of Scannable Binary Objects. A fundamental problem in the asynchronous shared memory model is obtaining a consistent view of the shared objects. A naive approach is to simply read all of the shared objects one at a time. However, this might not return a consistent view. In particular, we might obtain a sequence of values that were never simultaneously present in all of the shared objects. So for example, let's say we begin a sequence of reads here and obtain the values 1 and 1 from the first two shared objects, and then some process comes along and writes 0 to the first shared object and 1 to the third shared object. Then we finish our sequence of reads, obtaining the values 1 and 1. And so we've obtained the sequence of values 1, 1, 1, 1, even though these values were never simultaneously present in all of the shared objects during our sequence of reads. A well-known way to address this problem is to use a snapshot object, which is a sequence of read-write registers called components of the snapshot. Snapshot objects support the scan operation, which simultaneously reads all of the components. Each of the components can be written to independently with the update operation. So for instance, you could write 2 to the first component of this snapshot object with an update 1 write 2 operation. Snapshot objects were originally formalized by Efek, Atiyah, Dolev, Gaffney, Merritt, and Shavit. And since then, they've been used in implementations of obstruction-free consensus, bounded timestamping, among other things. A generalization of a snapshot object is a scannable object, which is a sequence of objects, again called components, that each support a read operation. Scan, again, simultaneously reads every single component, and we can still apply operations to each component independently. The components of a scannable object aren't limited to read-write registers. A component can support operations other than just read and write. So for example, let's suppose component 2 of this scannable object here is a test and set object. Then we could use the update to test and set operation, which would both set the value of the second component to 1, and it would return the value 0. So in particular, update operations on scannable objects can return values as well, unlike in the case of a snapshot object. A known issue with existing implementations of scannable objects, and in particular with existing implementations of snapshot objects, is that they use a lot of space. So for instance, many implementations of a K-component scannable objects use base objects that are large enough to store entire views of the object, which becomes impractical if K is very large. Other implementations require significantly more than K base objects. The point is, there's lots of space overhead in existing implementations, and we want to understand the space overhead better. So in this project, we begin this investigation by considering scannable binary objects, whose components are 1-bit objects. So what can we do with a 1-bit object? A 1-bit object stores a value that is either 0 or 1, and there are 8 possible operations that can be supported by a 1-bit object. 4 of these operations don't return anything. For example, we've seen write 1 changes the value of the object to 1. And another example is the flip operation, which changes the value of the object to 1 if its initial value was 0, and changes its value to 0 if its initial value was 1. The other 4 operations affect the value of the object in the same ways as the 4 on the left, but they also return the value that the object had before the application of the operation. So for example, the test and set or TAS operation does the same thing as write 1, in that it sets the value of the object to 1, but it also returns whatever value the object had before the task was applied. So the question that we explored in this project is, how many arbitrary 1-bit base objects are needed to implement an n-process k-component scannable binary object? In some cases, this problem is very easy to solve. For example, let's suppose we wish to implement a scannable binary object with k components, each of which is a test and set object. There's a wait-free implementation from k test and set base objects. Let's call them t1 to tk. In particular, we can use the simple double collect algorithm by these 6 authors from before. In this algorithm, the value of component I is stored in the base object ti. So to perform an update to component I, we simply apply the given operation to the base object ti. To scan, we simply read all of the base objects one by one until we see the same sequence of values in all of the base objects twice in a row. Since a test and set object can't return to the value 0 once it is changed to a 1, a scan needs to read all of the base objects at most n+1 times, and this is why this algorithm is wait-free. Unfortunately, this simple implementation does not work if the components can change back and forth between 0 and 1. If a 1-bit object supports an operation that changes its value from 0 to 1, and it supports an operation that changes its value from 1 to 0, then we say that the object is non-monotonic. So what if some of the components are non-monotonic? Can we still come up with an implementation in this case? In fact, we know that there is a lock-free n-process implementation of a k-component scannable binary object from n plus k base objects, even if some of the components are non-monotonic. The algorithm that we give in our paper is a modification of the double collect algorithm that I just discussed, and it isn't particularly interesting, so I won't describe it here. We also consider a special class of implementations in our paper called single updater implementations. In a single updater implementation, only process P0 can do update operations, while the other processes can only do scans. In the single updater setting, there's a very easy implementation from 2 to the k instances of 1-bit base objects. So this is better than the general upper bound on the previous slide when n is sufficiently large. Now I'll outline the main contribution of our paper, which is a lower bound on the space complexity of scannable binary object implementations. That is, we want to answer the following question. How many 1-bit base objects M are required by a linearizable n-process implementation of a scannable binary object with k non-monotonic components? So instead of giving the formal statement of our lower bound, which is a bit messy and confusing, I'll show you what the lower bound looks like on a graph. So here's how the number of required base objects M on the y-axis is related to the number of processes N on the x-axis, where the number of components K is just some fixed constant. The red line is our lock-free multi-updater upper bound of n plus k base objects. The purple line is the single updater upper bound of 2 to the k base objects. And the blue line is our obstruction-free single updater lower bound. The graph is divided into several sections by these dotted lines. The section on the left is between n equals 3 and n equals 2 to the k minus 1 plus 2. For this range of n, we show that an implementation requires n plus k minus 2 base objects. Then we see that the line flattens off for one process, so our lower bound effectively loses a base object. And in the next section, between n equals 2 to the k minus 1 plus 3 and n equals 2 to the k minus 2 to the k minus 2 plus 2, we show that n plus k minus 3 base objects are necessary. This pattern continues until finally we reach n equals 2 to the k minus 2. And at this point, we show that 2 to the k minus 1 base objects are required. So on the left side of our graph, our lower bound very nearly matches our multi-updater upper bound, whereas on the right side of this graph, our lower bound very nearly matches our single updater upper bound. I want to emphasize that our lower bound applies to obstruction-free single updater implementations. This means that it also applies to lock-free and wait-free implementations, since every lock-free and wait-free implementation is also obstruction-free. And it applies to multi-updater implementations as well. So our lower bound is actually very strong. So that's what our lower bound looks like. Now I will briefly go over some of the techniques that we use to achieve the lower bound. I'll begin by briefly talking about covering arguments and why we couldn't use this approach for our lower bound. So covering arguments are probably the most common technique for obtaining space lower bounds that you'll see in the distributed computing literature. They were first used by Burns and Lynch to prove a lower bound on the space complexity of mutual exclusion, and since then they've been used to prove all sorts of things. We say that a set of processes covers a set of base objects if, for every base object in that set, there's a process that's poised to apply an operation that will overwrite the contents of that base object. So in this case, where P1, P2, and P3 are poised to write to B1, B2, and B3, we would say that the processes P1 to P3 cover the base object B1 to B3. If we allow all of the covering processes to take their next steps, they obliterate the information stored in the covered base objects. This is called a block update by P1, P2, and P3. A typical covering argument uses induction to show how to obtain a configuration in which a bunch of base objects are covered, and the number of base objects that are covered gives us a lower bound on the space complexity of whatever's being implemented. So the first problem with trying to use a covering argument for our purposes is that the best lower bound we can achieve with this approach is n. So if we have n processes, they can't cover any more than n base objects. To obtain a lower bound of n plus k, which is what we want, we'd need a different technique. There's another slightly less obvious problem in that the effects of some of the operations on a one-bit object can depend on the initial value of the object. For example, if P1, P2, and P3 are poised to apply a flip operation to B1, B2, and B3, then the effects of the block update by these processes actually depends on the contents of B1, B2, and B3. This is a problem because we can't use the block update to overwrite the contents of these base objects as we do in a traditional covering argument. So now I'll give a high-level overview of the technique that we use to achieve our lower bound in the paper. So our main technical lemma looks like this. We show that there exists a set of L base objects called BL. L is some parameter here. The exact value of L isn't important to get the intuition of the lemma, so I will leave it undefined. Along with this set of base objects BL, there's an execution alpha L from the initial configuration C0 that satisfies the following nice property. So after alpha L is done, let's say we're in this configuration C, then for every execution from C that does not involve the last L scanners, and in which the updater P0 doesn't touch the kth component of the object, nobody changes any of the base objects in BL. So effectively after C, the last L scanners stop taking steps, and the base objects in BL stop changing, as long as the updater doesn't touch the last component of the object. So let's see what this looks like graphically. Let's say that O1 to OK are the components of the scannable binary object that we want to implement. And let's say that these are the M base objects used by some implementation for the processes P0 to Pn-1. So when I found this configuration C, what exactly does this mean? It means that as long as the updater P0 doesn't touch the kth component, okay, and as long as these processes don't take any more steps, then these L base objects stop changing. So effectively, I can remove the kth component, these last L scanners, and these L shaded base objects, and I'm still left with a correct implementation. So to obtain the final lower bound, we apply this idea repeatedly until there's only two processes remaining, the updater P0, along with one of the scanners P1. And we're left with an implementation of a K prime component scannable binary object, where K prime is some value less than K. So it's not hard to see that we need at least K prime base objects to implement this scannable binary object. If we had fewer base objects, then there wouldn't be enough space to represent all of the possible values of the object. So in the paper, we improve on this slightly, and we show that the implementation must use at least K prime plus 1 base objects. So these base objects plus the n-2 base objects that we discarded gives us a lower bound on the original K component implementation. So there are two major questions that arise from this project. First, can we prove our lower bound or something close to it for larger values of n? Since our lower bound technique applies to single updater implementations, we can't do any better than 2 to the k base objects, which is our single updater upper bound, unless we adjust our approach. So we would need to consider more complex executions that have concurrent update operations as well. It's also possible that we could use a stronger progress condition like lock freedom or wait freedom to improve our lower bound. The second research direction to consider is examining implementations of scannable binary objects with larger components, so thinking beyond just scannable binary objects. Thank you very much for listening, and enjoy the remainder of the conference.